Analysis of variance. So as said, we are continuing the hypothesis testing, and it is not quite easy to understand that we did hypothesis testing. It's again on this side. Okay, so we did now comparisons between groups. So we had two groups and we compared them against each other. Whether this was a before and after condition, and we compared two chronological conditions, or we compared two independent groups. We did hypothesis testing between two groups. Now we're getting in a more specific scenario where we have more than two groups. That's essentially when you think analysis of variance. So you have three or more groups, and you basically have, and this is a characteristic, you have a scale continuous variable on the y-axis, and you have a nominal categorically independent variable on the x-axis. Nolan and Heinz provide here the example of the likelihood of a collision while merging using a bar chart, right, that we have seen. And when we talk about bar charts, this is always some form of percentage or fraction. Notably here, this time around, we also see a little marker of the inaccuracy, so the so-called precision of the estimate. So this is now a variability of this bar chart. And I mentioned when we talked about bar charts and proportions that we can also quantify the variability of proportions. This is one way of depicting that. Okay, so you have a likelihood while collision of merging, that's the dependent variable on the y-axis. You have a categorical independent variable with four different groups. You have a drive alone condition, you have a passenger condition, you have a video phone condition, the cell phone condition. When you look at those four groups, what would you intuitively think, how you would find out whether there are differences between those groups? Intuitively, when you look at it, you say like, okay, compare this against this, this against this, this against this, this against this, this against this. So you basically go one by one by one by one. There's a problem with that. And the problem is that you have a type 1 error, which is the error of you rejecting something that you should not have rejected with each of your tests. And that is problematic. Because if you have an acceptable alpha, and that's the acceptable type 1 error of 0.05. Right, I'm zooming in. So 0.05 is your acceptable type 1 error risk with one test. If you do in three groups, you have three comparisons. What's going to happen? Because each individual comparison will come with a 5% risk of making a wrong determination. So essentially, your probability of being correct is 1 minus this. But not only that, if you make this 3 times, your probability of being right is shrinking to 86%. So the inversely, your probability to be wrong is now increasing from 5% to 40%.
Please repeat that.
Okay. No, don't worry. It's important that you let that sink in and really kind of intellectually penetrate it, because essentially this is the reason why there's actually a test like that, because otherwise it would be super simple, right? Otherwise you would just go ahead. So we do this minus this, 1 minus this is 14. So this remains the same, right? So if we do this a couple of times, we do this 4, 5, 6, 7, 8, 9, 10, okay. we have a 5% probability with one test. Group 1 versus group 4. Driving alone versus driving with a passenger that is chatting with you is different. But it may not be different, and it may not be different, and that risk is 5%, that you are basically making an assumption, but you're making this assumption wrongly. You have a 5%, if you're rejecting this null hypothesis of there not being no difference, you still have a 5% risk that you're doing this hypothesis, that you're rejecting this null hypothesis wrongly. So you only have a 95% chance that you're right. Yeah? That's a 95% confidence interval. That's the opposite of making a wrong determination. You have these columns on that table where you have indeed wrong, or indeed different, or not different, and then you have making the determination to reject the null hypothesis and accepting the null hypothesis. You have a type 1 error and a type 2 error. Type 1 error, you're rejecting something that you should not have rejected. Type 2 error, you did not reject what you should have rejected. So now we're looking only at a type 1 error. So you may reject something wrongly. And this can just be by a random chance, because you draw your population in one group out of a population of really good drivers. And your second condition, your second group was just, I don't know, somebody who just learned driving. That is chance, right? Error just for some random chance. And the type 1 error basically means to protect you from making this wrong prediction, and quantifying that gives you the probability with which you're rejecting, but you shouldn't have. And the 5% is wrong. So you're only 95% certain. Each of these tests, you're comparing now, you have 3 groups. You're comparing 3 groups against each other. Group 1 versus group 3, group 1 versus group 2, group 2 versus group 3, 3 comparisons. With each comparison, you have a 5% risk. And with each comparison, you're only 95% correct, likely to be correct. So these are mutually exclusive events. They're independent from each other. So each of those contributes the equal risk. And the way you calculate it, and we did that with the die, rolling the die, right? Rolling the die is 1 out of 6. That's, what is that, 60%, 60 something percent. Same story, with independent events, you're multiplying all 3. So you do 0.95 for being correct, multiplied by 0.95, multiplied by 0.95. That's this, multiplied to the power of 3. And then 1 as being the absolute truth, either wrong or not wrong, minus the probability of being correct, gives you the probability of being incorrect. Make sense? And now, if you carry this further, let's say up to 9 comparisons, your probability of being incorrect is increasing up to 0.37. So that's 37%. You're incorrect with a probability of 37%. Nolan and Heinzen even go further. They even show a projection up to up to 21 comparisons. So if you have 7 different groups and 7 different means that you compare, you have 21 different comparisons to make. This probability essentially is you're actually more likely to make a type 1 error than not making type 1 error. That is actually greater than 50%. 50% would be flipping a coin. Here you almost certainly have an error in there. So that's why the ANOVA is just a wonderful way to analyze data, to give you and allow you to test against the null hypothesis that at least one of these groups are different from another group. So now it's essentially just getting more complicated. So you have with a STAT test and the one sample t-test. It's back again. With a STAT test and the one sample t-test, You have one sample that you compared against your population mean. With a t-distribution and the paired sample t-test and the independent sample t-test, you compare two samples. So now you're just comparing more samples. I'm not sure I understand the analogy to the Swiss Army knife, but it means to say that it becomes more complex, and you need to think of things a little bit more holistically. And that's essentially what the ANOVA means to do. So just again, you have one sample where your mu and your sigma is known. You have one sample and only the mu is known, then you basically come to a one sample t-test, and comparing two samples, you have a t-test. If you have three or more samples, you use an F statistic. And all of this comes together. So essentially, when you think of the t-distribution, only the set distribution was reflected when you were the sample size of 500. You remember where the 5% alpha was at 1.96? This is in a t-distribution at a sample size of 500 or towards infinity. In practical terms, you get away with as soon as your sample size is 30. But generally, it basically approximates the set distribution. So these two are basically intertwining as soon as the sample size is really large. If you have three or more samples, you put together now all your distributions, and you come to an amalgamated distribution where you compare the means and the variability between those means, because that's essentially what the F distribution is. So you have now a variance within each group. So you have a standard deviation. You remember with the independent sample t-test, we quantified the standard deviation and this pooled variance between both groups, and we put weight according to the size of the respective sample on that estimate of the pooled variance. Now we have variances within those groups. So each individual entry within the group contributes to an overall variance within the groups, and we have variances between the groups. So each individual mean, if we have 7 groups, we have 7 different means. And there is variance between these 7 means. And the example that we will do today, and I'm jumping a little forward here, because it's just easier to explain it graphically. We will be doing an example studying a sample from 4 different societies, and we will be comparing these 4 societies. So now, you have here a variance within a group. That means that we have here a group mean, and we have individual scores. These individual scores contribute an individual deviation within the group. Squaring this individual deviation will basically get you to a sum of squares. Dividing that by the degrees of freedom within that group, which is 4 minus 1 would be 3, gets you to a variance within the group, within one group. But now you have 4 different groups that basically all contribute to this variance within the groups. And then you have a variance between the means that basically is the variance of each individual mean from the mean of means that is depicted here, which is the grand mean. That's how it's called, GM, grand mean. So this grand mean essentially gives you then a deviation to each individual mean. Squaring this, summing this, gets you the sum of squares. Dividing it by the degrees of freedom of all the means, which is the groups minus 1, which would be 4 minus 1 here, gets you to the degrees of freedom groups of between. Dividing now your sum of squares by the degrees of freedom gets you to the variance. And that's what the F calculation is. So we're working now with an F distribution, which essentially is a distribution. It's unimodal, amalgamates basically the within variability and between variability, and distributes unimodal, positively skewed to the right. The principle is the same. It looks like more numbers. It's not that complicated. But basically, we determine one critical F, and if our calculation of the F exceeds that F, we're rejecting our null hypothesis, which is that none of these groups are different from one another. And once we know one of these groups is, at least one of these groups is different from another group, by exceeding that critical F, we're rejecting the null hypothesis, and then we need to figure out which group. And that's when we come to what is called post hoc testing. So post is clear, hoc is Latin, stands for event. So it's post-event testing. So this post hoc testing essentially allows then a group comparison between each individual group under a restriction of the p-value and a minimization of the acceptable type 1 error. So you will be more cautious. You know one is different, but you will be more cautious in your interpretation because you want to avoid that you're rejecting something you shouldn't have rejected. Good, but we get to that in a second. Good, so variance between groups divided by variance within groups gets us to an F. This F notably is quite important to keep in mind also when it comes to regression analysis, and will probably, if you further your education and you learn more statistics, you will hear F statistics quite more frequent. ANOVA is done in principle in two different shapes. Again, where's that always coming back? I hope I'm sharing the right screen. Okay. So we have types of variance. There's a between groups and the within groups variance. Between groups are different groups, and we're comparing different groups where you basically have independent groups. So you basically, each participant is in one group, so no repeated samples. Whereas a within groups analysis, types of ANOVA, we talked about that already. Types of ANOVA, between groups, each individual participant basically is part of a different sample. So your dependent variable is a scale continuous variable. Your independent variable is a nominal categorical variable with different levels. Each level is a different group. Each participant is in a different group, is assigned to a different group. Within groups, you have each participant goes through the different levels of your independent variable or your condition. So in the example of likelihood of collision, you basically have 4 different conditions. You have a likelihood of a crash, that's your dependent variable, which is scale continuous, and you have independent variable, that's the driving condition. If it's between group, individual participant in each of these groups. If it's within groups design of ANOVA, each individual goes through all 4 conditions, and you're following that individual, and you estimate the likelihood of collision of the driver driving alone, the likelihood of the driver driving with a passenger, with a video phone, or with a cell phone. And don't ask me why cell phone and video phone is here depicted in that fashion, because a video phone would distract me much more than a cell phone. So I'm not really sure why that is. But that's a different conversation piece. Okay, is this clear? In principle, right? It's simple. No? Any questions? No? It's fairly simple. It's a continuation of where we've been, trying to minimize the error that we make by essentially using an intermediary step where we say, okay, so we're quantifying the probability of one of these groups being different. And once we know at least one of these groups are different, then we'll basically do the multiple comparisons, and we're being a little bit more cautious about the type 1 error. That's holistically, more globally, how we're looking at this. Good. one-way ANOVA. So we are only doing one way between groups and one way within groups ANOVA. We are doing these two only with one way. That means there's only one dependent variable. So only two levels of one variable will determine the independent variable and will determine that dependent variable. If you add additional variables, you make it a two-way ANOVA. With three, you make it a three-way. With four, you make it four-way. You get the picture, right? So you basically, you have different approaches how you can hypostatic approach an ANOVA. ANOVA is a very versatile statistical method. For each of any form of ANOVA, you make assumptions. The assumptions is a random selection of samples, as it always is. It was the same assumption for hypothesis testing with every parametric test that we did so far, with the Z distribution, with the T distribution. Same assumption. A normally distributed sample, we're only doing parametric tests, except for the chi-squared test. We're only doing parametric tests, non-parametric tests. The chi-squared is non-parametric, but that's for further statistical education that we do. And the third and last assumption is homoscedasticity. That's a little bit of a thumb breaker, I'm aware, but take it apart. Homo means equal. Scedasticity is scedastic, is the variability. So you have equal variability, equal variance, or not equal, but somewhat comparable between those groups. At least none of these variances should exceed any other variance by more than 20%. So it should be somewhat comparable. Homoscedasticity is also important for regression analysis. So I'm flagging the topic. This will also be on the quiz. So homoscedasticity is comparable variability throughout your groups. And for regression, it's over the entire range of available data. Heteroscedasticity would be the opposite, which means there's variability in your variability, meaning the variability changes between the groups or is different between the groups. The 6 steps are the same as they always are. We're identifying the population, we're identifying the distribution, we're making our assumptions. We're stating a null and the research hypothesis. Null hypothesis, all these groups are identical, are similar, are the same. Research hypothesis that at least one is different from one of those others. So we determine the characteristics of the comparison distribution, which is our F statistic. So we're estimating on our F statistic where the critical value is, where it's located. We find a reason why we use ANOVA in the first place. We're determining our critical value and the cutoff, and then we calculate the test statistic. We're calculating variance between those means divided by the variance within. And then lastly, based on this derived F score, we are either accepting or rejecting the null hypothesis. Simple, right? Same procedure as it always was. The calculation is a little bit different. So we have now a spreadsheet that I have given to you. This spreadsheet contains example 12.1. So essentially what it shows is we have the so-called dictator game. The dictator game is basically a game where each of the players in a group, the first player gets a certain amount of money, which equals the daily pay of that player, the daily salary of that player, of that country, of the society, and the percentage of which the player shares with the other player will basically be considered a fairness score. It's debatable game, but okay. But basically, it will be used in this research. It was used to determine the fairness and the equality principle in those 4 societies that were studied. So it was foraging, farming, natural resources, and industrial societies. So these 4 populations essentially lead us to think we need to compare them. using a one-way between groups and over because it's independent societies. So these 4 levers of our nominal variable society will essentially be used to estimate the differences. So we're basically making, okay, so we're formulating the 3 assumptions, which are normal samples, random samples, normal distribution, and homoscedasticity. We formulate the null hypothesis that basically at least one, or on average, all are the same, and the research hypothesis, at least one will be different from another society. Next, we need to quantify the decrease of freedom. That's the characteristics of the comparison distribution. And if we quickly look now in the spreadsheet, so the calculation of the spreadsheet for an ANOVA is actually quite, it's a little bit more complex. Now I have it here, okay. So we have, just by looking at this with the naked eye, we're seeing an average that kind of differs between the societies. We have 4 different means, which points towards there may be differences. So it seems just with the naked eye, we see already foraging is somewhat lower as compared to industrial. That means that the higher the society level in terms of civilization level, I guess, the more fairness will be predominant. That could be one possible conclusion. So we have not degrees of freedom to determine. So we have degrees of freedom between. And we have degrees of freedom within. Degrees of freedom are calculated as the number of, for between, are calculated as the number of groups minus that one that can be dropped in the knowledge of the sum of squares. So we have 4 groups. The degrees of freedom of 4 groups would be 4 minus 1. So that's 3. The degrees of freedom within, we have 4 participants in foraging, we have 3 in farming, 3 in natural resources, and 3 in industrial. That's 4, 7, 10, and 13 for all 4. These are the individual participants. 13 minus the number of groups, and this is important because each individual group has an individual degree of freedom. So the degree of freedom of foraging would be 4 minus 1, that's 3. Farming is 3 minus 1 is 2. So we have 3, 2, 2, and 2. So that's 3, 5, 7, and 9. So degree of freedom is alternatively formulated as 13 minus 4 groups.
Where did 13 come from?
These are all the entries. So we have 4 here. 3 is 7, 10, and 13. So 13 minus 4 gets you to 9. Because it's 4 groups. So you have a degree of freedom for foraging would be 4 entries, 4 participants minus 1, that's 3. You have farming, you have 3 minus 1 is 2. So you have 3, 2, 7, 9. So it's 13 minus 4. This is just a simplified way to express it. So 13 minus 4 gets you to the degrees of freedom within. And now lastly, we have a new one. We have degrees of freedom total. And this is a little bit more complex because this puts now degrees of freedom between and degrees of freedom within together and basically adds them up to 12. But that's at this point not relevant to be determined. So now we need a couple of things. So we have the degrees of freedom. So we have 3 levels of, if there are 3 levels of the independent variable, it would be only degrees of freedom would be 2. For our society example, it's 3 because it's 4 groups. 4 minus 1 is 3. If there's a total of 20 participants in each of the 3 levels, there would be 20 participants minus 4 groups. Because degrees of freedom minus 3, sorry, it's 3 levels. So it's 20 minus 3 would be 17. That would be degrees of freedom within. Now this is shown here. So you have degrees of freedom 1, 2, and 3, up until degrees of freedom of the last group. So this sums up to degrees of freedom within. So if you have 20, you can also take the whole number of participants minus the number of groups, gets you to the same result, logically, right? Okay, so this is the determination of the degrees of freedom. And now it's getting a little trickier. So we know now our degrees of freedom. We know there's 3 and 9. Between the 3, within is 9. Let's go back to review the formula. For the calculation of the F, we need the variance between the groups and the variance within the groups. So the variance between the groups, that's our numerator. Variance within the groups, that's our denominator. So degrees of freedom between will determine now which column you use. So you have here in the F-score table, you have columns that are basically representing the degrees of freedom in the numerator. That's between groups, degrees of freedom between. Then you have degrees of freedom in the denominator in the rows. You have 1, 2, 3, 4, 5. You have 1, 2, 3, 4, 5. And these blocks with the corresponding alpha levels. So when you have a degree of freedom of 3 and a degree of freedom within of 9, you're going in the column of 3, then you go all the way down. So here's 3 until you are at a degree of freedom within of 9. So that's 3.86. So that's the critical F. Okay. I know it looks a little busy, but it's basically if you go systematically to understand what the numerator is, what the denominator is, you just have to, again, look for the right column, look for the right row, and then just read it from the corresponding alpha, the p-value that you're willing to accept. So now your critical F is 3.86. Now the last thing that you need to complete this is your F. You know the null hypothesis, all of these means are the same. The research hypothesis is that at least one of these means is significantly different from another mean. This is what you're quantifying in holistic global approach in the ANOVA. So the way you're doing this is essentially, and I walk you through the calculations. No, not here. That is also not what I want. This is what I want. You basically do this by quantifying the variances. The variances for different sum of squares. So you remember from the calculation of the standard deviation, you quantify the deviation by subtracting the individual score from a mean. You're squaring this deviation and you're summing this deviation up to get to the sum of squares. So now you have 3 different sum of squares that you want to get because you want to get to the variance. So for the variance, you need the sum of squares and the degrees of freedom. Sum of squares divided by degrees of freedom, and now you may understand why I was so diligent about the calculations of the standard deviation, because variance is sum of squares divided by degrees of freedom. Between group variance will be calculated as sum of squares variance divided by the degrees of freedom between. Within groups as the sum of squares within divided by the degrees of freedom within. Total in the same fashion. So the way you're calculating this is by calculating sum of squares between as the deviation of the mean minus the grand mean squared for each entry. Sum of squares within is individual x minus the sample mean, like the group mean, squared and summed. And the sum of squares total is the individual score minus the so-called grand mean. And we will get to what the grand mean is. So this is how you calculate your sum of squares. So now, if you, let's do this quickly. So we need, and that's the first step, we need to transpose our entries. And that's a little bit of a, no, wrong, not that. This. So we're transposing our entries. That's just, I'm just quickly doing this here. So we're bringing now this rather awkward wide format into a long format that makes it easier for us to calculate it. And now we basically can calculate quite simply what we need to calculate. So we have now this data brought into long format. If you want to know, as the first step, you want to know the grand mean. And the grand mean is here nothing but the average of all these entries, of all individual x scores. Next, you want to calculate the individual deviation from that grand mean. That's our sum of squares total. And that's quite simply done by, so this is x minus grand mean squared. That's basically this individual x minus the grand mean squared, and basically continuing this calculation all the way down and then summing it up. Oops. So important here is that you lock in the cells. Otherwise it will shift that formula. So basically that gets us to a sum of square here of 629, 629.1. That sum of squares is basically what the outcome of our total estimate is. Now we will need next, we need a within variability, and for this we're inserting this to the right, and we calculate now a sample mean, which is basically the average of each society that was tested. So we get here 33.25. We propagate this all the way down. We're calculating here again an average of these three entries. And oops, same here. And you can always change this shifting formula by basically clicking on paste values. So you always get, as soon as you paste any value that derives from a formula, you will basically get this little drop-down menu here where you can select paste values. And that will only copy and paste your actual value. So the average now is basically can be propagated all the way down without repeating that formula by simply calculating and choosing paste values. But sometimes in many situations this is quite helpful to know. So x minus m squared is now essentially what gives us our sum of squares within, because we are subtracting the sample mean of each of these groups. So each of these scores is we're calculating the difference of each individual score from the sample mean. That gets us, after squaring and summing it, to the sum of squares within. So if we're calculating by x minus the sample mean squared, gets us these individual sample means, and summing that up basically gets us to a sum of squares within, which notably is quite small. And this is then lastly completed by the so-called sum of squares between and the variance between. We're basically now calculating the sample mean minus the grand mean squared. What is the peculiarity of calculating that? And that's important. You need to preserve the sample size. So this needs to contribute individual entries that is consistent with the sample size within each respective group. So you have m minus sample mean m, sample size m minus the grand mean. That again needs to be logged in, squared. That gets us now our sum of squares between. And just squaring that basically gets us the last sum of squares. So now we have a sum of squares total, we have a sum of squares within, we have a sum of squares between. These three values are basically arithmetically interrelated because this and this equals this. So if I would want to calculate this total sum of squares, would be the sum of this and this. And this will be important for you to know for the homework, because that's going to be part of that. For a particular reason, not this. For a particular reason, because in the end of the day, not this. In the end of the day, so you want to calculate your F, which is the between groups variability divided by the within groups variability. And in the end of the day, what you want to fill out entirely, which this is the so-called ANOVA source table. And this is an important way of visualizing and summarizing this data, because that will give you an overview of all the respective components, but this will also be the table that each statistical software will provide you with. So they're basically all giving you exactly that table with the sum of squares, with the degrees of freedom, with the variances, and with the F. Well, it's a squared mean error, which essentially is nothing else but the variance. Yeah, it's a mean squared error. But essentially it is the variance. It's just calculated, and this is now, let's do our own little ANOVA source table. So we have now between, we have within, and we have total. And if we get sum of squares, so we have now between as 461, we have within as 167. We have the sum of these two as 629. We can now, with the degrees of freedom that we also know, so we know degrees of freedom between is 3, the degrees of freedom within is 9, the degrees of freedom total is 12. We can now calculate our variance. Let's call it variance, actually. This is now nothing else but the sum of squares divided by our degrees of freedom. Equally, for the within, we can calculate our within variance as sum of squares divided by degrees of freedom. And now it's just a stone throw away that we essentially get to the F, which is nothing else but the decrease of the variance between divided by the variance within. And that gets us to the F. And this is now this divided by this, gets us to 8.27. And if we remember now the F-score table, we have a degree of freedom in the numerator and the between groups variance of 3. We have within groups variance degrees of freedom is 9, which at an alpha level of 5% gives us 3.86. So we are significantly, we are rejecting our null hypothesis of none of these groups being significantly different. So we are going beyond our critical value of F. We're basically rejecting our null hypothesis. And we know that our type 1 error for the ANOVA is smaller than 5%. That's basically how simple it is. And I know it's arithmetically and you need to do quite a few steps of calculation, but in the end of the day, all that matters is really this ANOVA source table, and you need to get to this source table and each respective component of that source table. And this is essentially what will be part of the homework. So 2 slides I really want to flag. This is slide 20, that's the ANOVA source table, and slide 24, which basically shows you to each of these respective calculations. So here you have a more detailed explanation of what these respective components are, but they're basically consistent with what we've just seen. Here you have the m minus gm squared summed as the between groups variance, the sum of squares. Here you have the x minus m, that's the within groups sum of squares, and here you have x minus gm, like the minus the grand mean, that gives you the total sum of squares. You get the degrees of freedom, that's the number of groups minus 1 gives you the between groups degrees of freedom. Then here the degrees of freedom of each individual group summed up, and the total degrees of freedom is the total, the n total minus 1, which is, we had 13 participants, and 13 minus 1 gets you 12, which is the same as 3 plus 4 plus 9. Then we have the sum of squares between divided by the degrees of freedom between, gets you to the mean squared error or variance between, and here to the variance within. The ratio between variance between by variance within gets you to the F, which you utilize for interpretation of your test statistic. Any questions? Is it somewhat understandable what the principle is? I know it's a lot of steps in between. That's why I kind of rushed through it. Please rewatch the lecture recording and look at those spreadsheets. It will be very clear if you go through each step of those. It's really, these are the calculations and these are the respective components. You will have in homework 3, you will have to do a couple of calculations that basically will allow you, quote unquote, allow you to do more calculations in the ANOVA source table, but basically it will give you a practical example why that is relevant. Because nowadays you can run a lot of analysis in statistical software and you get these ANOVA source tables, but they need to be understood that you can draw solid interpretation out of them. Good. So this is the ANOVA source table, basically quantified and filled out, as we've just filled it out ourselves. So once you basically bring this all together, we know now that the ANOVA is telling us that the null hypothesis is wrong. At least one of these groups is different from another group. Now we're basically, so we're rejecting the null hypothesis.
That's always the case. Or is this just a weird example?
No, that was just the example. So if it's greater than the critical F, then we would reject. Otherwise, we don't reject. Because the critical F determines in conjunction with the calculated F, whether it's significant or not. Whether we reject or we accept the null hypothesis.
Sorry, can you that if it's greater than the critical F, then it'll be rejected, but what? But if it's not greater than.
If it's not greater than the critical value, we will accept the null hypothesis that none of these groups is different from the other. Make sense? Answers your question? So critical value comes from the F-score table. The calculated F is the one we calculated based on the source table and our calculations. And if it exceeds, we will reject the null hypothesis and we will accept the research hypothesis that says that at least one mean is different from another mean. Good. So compare the variance by dividing the sum of squares by the degrees of freedom. Divide the between groups MS by the within groups MS and compare it to the critical value in your F-score table. If the calculated F is bigger than the critical F, we have a significant difference between means, at least one. However, we also want to quantify the effect size, and the effect size is here quantified not with a D, not with Cohen's D. Now we're moving into the realm of regression in a way, because in regression, the R squared is essentially the amount of variability that is explained by a regression model from the overall variability in the existing data at hand. Also here, it is basically the proportion of variance in the dependent variable that is accounted for by the independent variable in the form of the sum of squares between. So we have a sum of square total, which is basically a reflection of our overall variability. So that's the variability that each individual score has to the grand mean across all means. It's the sum of squares between is basically the variability between the means. And it gives you overall an estimate of how much of that variability, the total variability, is being explained by just the variability of the means, and reflects how strong these differences actually are. In the end of the day, what it quantifies is the overlap. So if you have, where's that graph again? Yeah.
The sum of squares total is between X and I. What's the sum of squares total? That's between X and.
Sum of squares total is the individual X minus the grand mean. But let me find the graph. I'll explain. Where's my graph? There. So you have the sum of square total. So you have a grand mean. You have individual group means, and you have one grand mean. This grand mean is basically the mean of means. Is the mean of means, and that's basically the mean of all individual entries. That's this thick line, this bold line. The sum of square total is essentially the deviation of each individual point from that grand mean squared. So that difference, remember that was the first column we did, was X minus GM. So that's the individual contribution to the variability is quantified as the individual variability of each individual point to the grand mean. The between groups variability is basically the variability of each of these individual means to the grand mean. The more that varies, the larger your effect size will be, the more likely it is that you see difference between the groups. What works against it is the variability between those groups, because if there's a lot of variability in your individual groups, think of the way we looked at power and effect size. So the more overlap, the less power and the smaller the effect size. Remember that? So if there's more variability, you have more overlap. So this explanatory parameters, so like this variability within the groups to the grand mean as a fraction of quantified, no, wrong. The variability between each individual group means how well that explains the variability between each individual point and the grand mean will basically explain a certain part of this total variability. And the larger this explained part is, the greater your distance between the groups and the smaller your variability, and the smaller the overlap between these distributions. This is basically, this is 4 different distributions. And these are overlapping to some extent. And you mean to quantify this with your variability, with your estimate of the variability. And you're comparing this in the light of the variability between those means. And this ratio gives you an idea how strong the effect is of whatever group difference you have. Yeah? I know it's conceptually not entirely easy to digest, but I guess this graph is gold in terms of understanding. It's actually a very neat graph. So. Okay. R square. So the R square basically gives you an idea of how much these groups and the variability within those groups overlay, and how well the total variability is explained by just the variability between those means. And it's calculated as the sum of squares between divided by the sum of squares total. So it's 0.73, which is a considerably large R squared. As you can estimate, this is a proportion. So you can convert this R squared also into 73% of the variability is explained by the variability between those means. That means that there's not really a substantial amount of variability within the groups, which is true because we see 461 versus 167, right? Proportionally, between groups, the differences between the groups contribute more to the overall variability. Therefore, the effect size is large. And not only is it large because I say so, it's large because the conventions say so. So we have small effect sizes as 0.01 to 0.06. We have medium effect sizes from 0.6 to 0.14, and everything greater than 0.14 is large. Any questions to any of this? I know it's not simple, and I think I kind of warned you. Like I know it's quite a learning curve, but let it sink in and really review the material and go through the lecture recording again, because next week within groups and over, we're hitting running ground. So that will continue right away. Good. So once you have an ANOVA in place, you essentially have now a rejected null hypothesis in our case. If it's not rejected, then you will not even continue your analysis. You will not do group-wise comparisons if your ANOVA was not significant. The only reason why you would still do it is because you had in your study design or in your analysis plan predefined pairwise comparisons. So if you said, let's go back to the likelihood of the driving conditions. You have 4 different driving conditions. You drive alone, you drive with a passenger, you drive with a video phone or a cell phone. You said, I want to study this prospectively with 100 people. And I'm planning to compare cell phone versus driving alone. And you have defined that when you designed the study, then you will still do this analysis, irrespective of what your ANOVA shows. If this is not predefined, you will only do these tests when the ANOVA is significant. because you know already, if it's not significant, you know that none of these groups is significantly different from each other. That's what the ANOVA allows you to interpret. The post hoc tests that we will discuss, and there are more, there's, I think there's like 5 or 6 to be found that allow for post hoc testing. The 2 that we will discuss is a Tuckey honest significant difference test and a Bonferroni pairwise comparison test. Tuckey essentially calculates Tuckey's Q, and this is basically a pairwise comparison. So you take now, so you have 3 groups. You have group 1 minus group 3, group 1 minus group 2, group 2 minus group 3. That's 3 comparisons. You calculate for each of these comparisons your HSD-Q, your Tuckey honest significant difference Q, by calculating M1, so that mean of that one group minus the mean of the other group, and here we are with hypothesis testing, right? Divided by a standard error of the mean, which you quantify with your variance divided by your sample size. Gets you to HSD-Q. And to bring another table into the equation and to make it really easy, there's a Q table that basically allows you to now create and interpret your deriving Q. So if you calculate in your pairwise comparison a Q that is essentially exceeding one of these different critical Qs, you will essentially interpret this group to be different. Why is it a different table? Why is it not the T table or the SET table? Because you want to be more restrictive on the acceptable type 1 error risk. So this is why you utilize a different table and you use different critical Qs for your hypothesis testing. Any questions on the Q? It's kind of simple, right? It's nothing else but hypothesis testing, except for you're using a different standard error of the mean, quote unquote. So you calculate group 1 mean minus group 2 mean. You divide it by standard error of the mean. That's basically an MS within, which is your variance within, divided by your n square rooted. Gets you to your honest significant difference Q, and that you basically that comparison you basically interpret as being significantly different if your Q exceeds a critical value on the Q table. The other post hoc test that we will be briefly talking about is the Bonferroni test. Is a post hoc test that basically still utilizes a p-value in a pairwise t-test. So you do an independent sample t-test, you get a resulting p-level, but the acceptable alphas will be adjusted for the number of comparisons. So if you have 3 comparisons, the only p value that you will accept as significantly rejecting the null hypothesis of these 2 groups not being significantly different will be set at 1.7%, not at 5%. So basically you are lowering your alpha and the acceptable type 1 error rate with each comparison that you conduct. So that's the Bonferroni test. Any questions on Bonferroni? Then I'm finished for today. Have a nice evening. I know it's not, I'm well aware, I know it's not. It's something that needs a little bit of digestion, but it's an important test. And you will definitely be exposed to it again. It wasn't the last time you heard about it. All right. Have a nice week and see you on Monday.